Look at the answer on your screen. Left side, 2 out of 10. Right side, 9 out of 10. Same physics knowledge, completely different exam result. Picture this. You're sitting in the exam hall, staring down a heavyweight physics 0625 paper, and you hit a massive question on forces and momentum. Your mind goes blank, the panic sets in, and that clock is just totally merciless. Well, today's explainer is going to completely eliminate that panic. We're breaking down the exact strategies, the core momentum equations, and the high-mark frameworks you need to absolutely dominate this paper. Seriously, look at this before and after shock. It's kind of crazy, right? On the left, we've got your typical low-scoring attempt. It's super vague. The student hasn't bothered to write down the base equation, and the final number is just sitting there completely naked without any units. You're literally bleeding method marks here because the examiner cannot follow your reasoning. But check out the right side. This is a top-band 9 out of 10 answer. It grabs maximum points just through pure structure. The formula is explicitly stated, values are subbed in, carefully accounting for the vector direction, and the correct units lock it all in. Same brain power, entirely different grade.
Now, before we get into things crashing into each other, we have to look at this train diagram. It's a perfect illustration of forces and equilibrium. See that massive concrete balancing weight? 10,000 newtons sitting 5 meters from the pivot, just to counteract the load way out at 25 meters. It's absolutely crucial to get this. Before you can understand moving forces and dynamic collisions, you have to understand how forces balance in a straight line. If you can't balance the static forces here, those dynamic ones are going to be a massive struggle later on. And this brings us to exactly why ordinary revision totally fails. Students constantly make these painful, completely avoidable mistakes. Look, memorizing the textbook is not going to save you if your answer lacks units or if your conclusion has zero data to back it up. The Cambridge Examiner reports highlight these exact same errors literally every single year. Rounding numbers way too early in a multi-step calculation that completely throws off your final answer, or maybe using the wrong variables, or just writing these vague paragraphs that sound smart but contain zero actual scientific reasoning. Okay, so let's lock down a massive quick win right now. Momentum is mass times velocity, or P equals mv. But here's the thing that separates the top-tier students from everybody else. Momentum is a vector. And because it's a vector, its direction is absolutely critical to getting the math right. It doesn't just have a size, it has a specific direction in space. Forgetting this during a collision calculation means your numbers are going to be completely backwards. And hey, in a moment, I'll show you the exact examiner clue that changes the answer completely. But first, you need the framework that makes that clue super obvious. So how do we bulletproof your answers? You're going to apply this 4-step high-mark framework to literally every single calculation you do. Step 1, concept. Just write down the raw equation like P equals mv. Step 2, evidence or data. This is where you substitute your numbers in clearly. Step 3, scientific reasoning. Show the logical steps of your algebra. Don't skip steps. And finally, step 4, examiner wording. Lock in that final calculated number with the correct significant figures and units. If you do this, it's virtually impossible for the examiner to take your method marks away. We're going to apply this framework in just a second, but listen up because this next bit is huge. Missing the hidden clue I mentioned earlier means your final calculation will be entirely wrong, even if your algebra is flawless. Like 0 marks wrong. So stick with me here as we build the foundation to actually sport it. Right, so this brings us to the first major rule for dynamic systems, the conservation of momentum. It's an amazingly simple idea. In any straight-line collision, assuming there are no outside forces messing with the system, the total momentum before the impact perfectly matches the total momentum after. Whether 2 trolleys are smashing into each other or an explosion is pushing 2 objects apart, the overall momentum of that closed system doesn't change. It simply gets transferred around. Think of it like a cosmic accounting book that always balances. So, let's see how that rule turns into our core equation. Looking at object 1 and object 2, the left side shows the total momentum before the collision. We use u for initial velocity. So, mass 1 times initial velocity 1 plus mass 2 times initial velocity 2. Then, on the right side, we've got the aftermath. We use v for final velocity. Mass 1 times final velocity 1 plus mass 2 times final velocity 2. This equation is your absolute best friend. Write the whole thing out in step 1 of your framework, and boom, those method marks are secured. Okay, escalating things a bit, let's tackle a harder concept that trips so many people up: impulse. Impulse actually gives you 2 completely different ways to solve a problem, and trust me, the exam will test both. The equation is Ft equals mv minus mu. Basically, you can calculate impulse by multiplying the force on an object by the time it acts. Or you can just calculate the raw change in the object's momentum, its final momentum minus its initial momentum. Both methods give you the exact same thing.
All right, here is your interactive challenge. I want you to pause and look really closely at the student's calculation. It looks totally correct at first glance, right? But there is a massive, fatal error here that will cost you the grade boundary. They're trying to find the impulse of a 50-kilogram object hitting a wall at 10 meters per second and bouncing back at 5 meters per second. They wrote, impulse equals mv minus mu. So 50 times 10 minus 50 times 5 equals 250. Seems completely logical. The formula's there, numbers are plugged in, but guess what? It is fundamentally wrong.
Did you catch it? Here's that hidden examiner clue we've been teasing. Momentum is a vector. Remember? That means if an object bounces back, that second velocity has to be a negative number. Even though we're only looking at straight line motion, you absolutely must assign positive and negative values. If hitting the wall is a positive velocity, bouncing back in the exact opposite direction is a negative velocity. The student in the last slide just tossed in a positive 5, completely ignoring the physical reality of what's happening.
Let's look at the examiner style correction using our framework. See how factoring in that negative velocity changes everything? The flawed calculation gave us 250, but the top band calculation? The final velocity v is negative 5. So the equation becomes 50 times 10 minus 50 times negative 5. And what happens? That double negative turns into an addition. 500 minus negative 250 actually equals an impulse of 750. By missing one tiny negative sign, that first answer was off by a huge margin. That right there is exactly how Cambridge tests if you really understand vectors.
So before you rush off to the next question in the exam hall, you've got to run a final mental check. Always do a practical sweep of your answer to make sure everything perfectly matches Cambridge standards. Did you clearly show your substituted values? Did you remember the negative sign for any rebounds? Are your units spot on, like Newton seconds for impulse or kilogram meters per second for momentum? And lastly, did you save your rounding for the very end of the calculation so you didn't mess up your significant figures early on?
Okay, so you now have the exact mathematical framework to calculate momentum perfectly. But here's the crazy part. A perfectly calculated answer can still lose marks if it's not presented exactly how the examiner asked. Your after-answer success depends entirely on the next command word framework. Do you actually know the exact difference between explain, describe, and evaluate in a Cambridge mark scheme? Because if you don't, you are leaving crucial marks on the table. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations, and click on the next explainer right now so we can master those command words together. See you over there.